I'm going to be explaining the second law of thermodynamics for my Chem 102 class. So the second law of thermodynamics says is that the state of entropy of the entire universe as an isolated system will always increase over time, and that the change in entropy of the universe can never be negative. So from that we can write that change in entropy of the universe is always greater than zero. Another way to rewrite this, or to expand on it, is that we can say the delta change in entropy of the universe is equal to the change in entropy of any given system plus the change in entropy of its surrounding, and that to be always greater than zero. So delta S surrounding, we can actually rewrite this as delta S surrounding is equal to the change in enthalpy of a system, because we're going to want to have everything in terms of the system. So if we plug this back into this equation, we'll get that the change in entropy of the universe is equal to the change in entropy of a system plus delta H over system over T. Now to make things look a little bit neater, we're going to multiply everything by T and by -1 so we can move stuff around. So negative T delta S universe is equal to delta H over system minus T delta S of our system. Now, here's where we can start relating entropy to Gibbs free energy. So if we take this and we set this equal to G, our negative T delta S universe, so G is our Gibbs free energy. So we're going to, from here, we're going to get delta G is equal to delta H minus T delta S. So this looks like something we know how to do. This is given to us. This is where this comes from. And another representation of Gibbs free energy is dG is equal to V dP minus S dt. So we're going to look at how we get that first. So first, let's look at this again. Let's get rid of the deltas. So I'll just rewrite this without the deltas. G is equal to H minus TS. So see, we have here derivatives, so let's take the derivative of that. So this is just going to be equal to dG minus equal to dH minus derivative of TS. So we're going to have to use chain rule here. So dG is equal to dH minus TdS minus SDT. Okay. So from here, we know that energy is equal to dH minus, or not dH, sorry, it's H minus PV. So let's take the derivative of this as well. So we're going to end up with dE is equal to dH minus P dV minus V dP. We do chain rule here again, but I just skipped it. So let's solve for dH. dH is equal to dE plus P dV plus V dP. So if we plug this in back into this equation, this one right here, we'll get something like dG equal to dH minus T ds minus S dt. And then to further expand on that, dg is equal to dH, which is also just dH minus P dV plus V dP plus P dV minus T ds minus S dt. So these cancel out, and this cancels out with this, and we're going to get dg, because this is actually just T ds. So we're going to get delta G is equal to V dP minus S dt. And what this equation tells us, it just says that that the second law tells us that entropy is pressure and heat dependent. So that's how entropy and Gibbs free energy are related. So from here I want to relate Kc and Kp. So Kc and Kp. So we know that if we're given a reaction, so AA plus BB is equal to CC plus DD. From here we can just easily figure out our Kc, which is just products over, or moles times concentration of products over reactants. So concentration of C to the C power, concentration of D, the D power, over the reactant side, so A, B, B. So we're going to need to remember this, because when we write this in terms of Kp is just the partial pressures of this. So we can rewrite it as Pc of C times Pd of D over P of A to the A power, Pb to the B power. So the relationship between these two is, first we look at our ideal gas, the formula for the ideal gases that we know, so PV is equal to nRT. So right here we have pressure, so let's just solve for pressure from here. So just rewrite this as P is equal to nRT over V. So what this accomplishes is that we have now N over V, and N over V is just really concentration, so concentration, and we'll call that C, and we can rewrite this as P is equal to C RT. So our Kp is going to be equal to concentration of C times RT to the C power, and do that for the rest of them. Concentration of D RT to the D power over concentration of A RT to the A power. Same thing for this, B RT to the B, lowercase b, B power. So we can actually rewrite this into a much neater form. We can factor out the RTs from the concentrations of everything. So what this will accomplish is that we're going to get back Kc, because as you will see, we'll get that the concentration of C to the C times D to the D over A to the A times B to the B power. This times we will factor out RT, so RT to the C plus D, RT to the A plus B. So see, this is exactly what our Kc is. So we can start changing things around. Okay, so our Kp is actually equal to our Kc times RT, and it's going to be the difference between these two, since it's one over the other. It's going to be these are negative exponents, so we'll just call that delta N, and N is the number of moles from the equation. So from here we can go back to the Gibbs free energy, and then relate that to Kc and Kap, and then back to standard Gibbs free energy. So we have that dg is equal to v dp minus s dt, and v and negative s, these can also be rewritten in a different way, where v is equal to the del g over del p, fix the t, dp, so keep the dp, and negative s can be rewritten as del of g over del of t, p, and keep the dt. So we're going to use this to relate delta G is equal to delta G standard plus RT ln of Q. And at standard temperature, or at standard standard state, we know that dg is equal to 0, so if we plug in 0 here and move stuff around, dg standard is going to be equal to negative RT ln of K, because we're in standard conditions. So standard conditions, we know that G standard is equal to 1 atm, temperature is 25 degrees Celsius, and N is equal to 1, which is our moles. This is all standard conditions. So we will look at a liquid to gas reaction at equilibrium for this. So for any given liquid, we can say that the Gibbs free energy of liquid minus standard Gibbs free energy liquid is equal to V liquid times P liquid minus P standard of a liquid, and we will call this equation I. Then for gases, it's going to be the same thing, but for the gases, G of a gas, I think this should be G standard, my bad, is equal to V gas, P of a gas, minus P standard gas, and this will be equation 2. So we know that from this PV is equal to nRT. We can also rewrite this in terms of gas or liquid, so we're going to choose to write V gas equal to nRT over P gas, and we'll call this equation 3. And so let's subtract equation 1 from 2. So this after combining like terms, we're going to get G of a gas minus G of liquid minus G standard of gas minus G standard of gas, G standard of liquid is equal to we know that Vg is nRT Pg, nRT over Pg times Pg minus Pg standard minus our VL, which has not changed, times PG, or PL minus PL standard. So this right here is actually going to be 0. And we can rewrite this right here as dPg, because it's just the difference in P. So, and we can also write this in like derivatives. So dG of gas minus liquid is equal to, or minus dG standard of gas minus liquid will be equal to nRT over Pg, and we'll get dP of gas minus liquid. So we can actually take this and integrate to get rid of our d's. So we're going to integrate everything. So just to speed things through, it can be integrated from gas, from liquid to gas, liquid to gas, liquid to gas. And what we're going to end up with is our Gibbs free energy equation. So this is actually just a change in Gibbs free energy from gas to liquid. So d, or delta G minus delta G standard will be equal to nRT, which are just constants, natural log of this over that, which is just P. We'll call that P star. So remember, we're in standard conditions, so our n is equal to 1. So that gets rid of this. And we can rewrite this as, or simplify it. dG is equal to delta G standard plus RT, natural log of P star. And we know that our P is equal to, from our Kp, it's the partial pressure of like the concentration to the power of C, PdD over PAA, PBB. And this is our Kp, or this comes from our Kp, and this is just equal to, it's a quotient constant, so it's equal to Q. So we can plug Q back in here. So delta G is equal to delta G standard plus RT, natural log of Q. And since we're in standard conditions, we know that delta G is 0. So 0 is equal to delta G standard plus RT, natural log of K, because Q is just K in under standard conditions. So if we write this again, delta G standard Gibbs free energy is equal to negative RT, natural log of K. And that's pretty much it. That's all we need.